Great, thank you for having us. It's great to be here. I should say that Scott Aaronson does not know any of the questions I'm going to ask him, so let's see, even though he's a superhero, he may not be able to answer all of them. But so I'm going to start off with, so I'm currently doing an internship at NASA Ames, and I'm a PhD student at Stanford. And I usually take an Uber pool to go to NASA Ames. And one time I'm in an Uber pool, and there's a fellow passenger, and it's pretty silent on the way there. But as we actually approach NASA, he sees the sign, and he asks me, "Are you a rocket scientist?" And I say, "No, I'm a quantum scientist." And then I proceed to get out of the Uber. So my question for Scott Aaronson is, if you're in an Uber pool and you're just about to approach your destination, and then someone asks you, "What do you do?" what would you say in like 30 seconds?
The usual description I use is I'm someone who studies what we can't do with computers that we don't have. That description served me well for the 20 years I've been in this field, although it may be becoming obsolete actually, which is a sign of how our field is changing. I should say that I've never actually thought of myself as a superhero, but I did like on Twitter when the Q2B people tweeted about they're going to ask me anything with this Tony Stark without the fortune or fancy suit, and someone replied, "Well, isn't Tony Stark without the fortune or the suit just some asshole?" So.
Thanks. So how to proceed from there? Well, so actually, Scott Aaronson is also a blogger, and as you may know, he has this famous blog where he talks about quantum computing and other things. So I'm curious, could you tell us a bit about the name behind the blog and how that relates to quantum computing?
It doesn't relate that much. I mean, okay. I saw Fiddler on the Roof a bunch of times as a kid, and I felt like, wow, I was somehow, meant to be in this sort of much more ancient world. It just sort of, but I sort of, I don't find that today, so I look for the closest thing that I could find, which ended up being academic computer science departments. But I was trying to maybe draw attention to the irony that, I feel like I'm 38 years old, going on 90. Like, my memory is terrible. I'm like incredibly old-fashioned in how I think about things. But then I also, like as many of us here, work on a type of computer that's sufficiently modern that it doesn't even exist yet. I just enjoyed that contrast, that juxtaposition.
Okay, great.
Yeah.
And so one thing in your blog is there's a blog post about this commercial in 2007 where there were these two models preparing for a fashion show in this commercial. And one of the models asks, but if quantum mechanics isn't physics in the usual sense, if it's not about matter or energy or waves, then what is it about? And the other model replies, well, from my perspective, it's about information, probabilities, and observables, and how they relate to each other. And the other model said, oh, that's interesting. And this was a printer commercial, and at the end, they said a more intelligent model for this printer. But the strange thing about this is that it's not strange the commercial itself, but those quotes that the models are saying was directly from one of your lecture notes on quantum computing. And in fact, in this lecture, you talk about a new sort of way to think about quantum mechanics, or a different way to think about quantum mechanics. So I'm curious if you could maybe explain a bit more about this different way of thinking about quantum mechanics and how it can help in thinking about quantum computing.
Okay. I think that one of the great effects that quantum information has already had on the world, and it doesn't even need to wait for the construction of useful quantum computers, is just giving us a much gentler route into understanding quantum mechanics itself. I think this has already had an impact. I mean, there are at many universities now, and including at UT Austin and at a bunch of others, there are undergraduate courses on quantum information science. I'm actually I'm going to fly back tomorrow to administer the final exam for mine. These courses don't actually require a physics background necessarily. It helps if students can know how to manipulate vectors and matrices. It helps if they've seen a complex number. It helps if they've done some classical programming, some classical algorithms. But after that, you're basically ready to jump in and sort of understand the conceptual aspects of quantum mechanics that are of most interest to people. What is this Bell inequality, right? What are the arguments for or against the many worlds interpretation? What is this quantum teleportation, and so forth? And you can just start immediately discussing those. You don't need any infinite dimensional Hilbert space. You don't, you can learn all of that stuff later. Right, and I like to say that quantum mechanics just becomes vastly simpler once you take the physics out of it. But then after you've learned these sort of different rules of probability that are underlie the world, you can then put the physics back in, should you choose to, and actually have a much easier time understanding it. I think that there was sort of a big mental block to teaching quantum mechanics this way because it is pretty much the opposite of the historical order in which these ideas were discovered, right? People really started with continuous classical physics and then put sort of one kludge after the next on top of it until finally by the late 1920s they realized, okay, what's really going on is nature somehow cares less about probabilities than about square roots of probabilities, right? And there's this different set of rules of probability based on these complex unit vectors and so on. And so for generations, quantum mechanics would be taught to physicists by sort of going through this whole story of the sort of one crisis of classical physics after the other until finally you get let in on the secret that it's all just vectors in Hilbert space. In quantum information, the nice thing is that we're not sort of bound to follow that. We can just let people in on the secret right away, in the first week, and then just explore what the implications are. So, I've seen, this is not just an abstraction for me. I'm actually doing this. A lot of my colleagues are doing it, and, we see firsthand that this is a really accessible route to quantum mechanics. It's physics, a lot of physics majors like it, but also, math majors, CS majors, sort of, anyone with just a little bit of math can then sort of actually understand something about quantum mechanics.
Great, thank you. And we've heard a lot about quantum supremacy recently, and I've heard that people have been proposing sort of new types of quantum supremacy experiments. So, for example, IBM talked about this pentatene molecule and simulating something more complicated than it. I've heard other ones. So what do you think about proposing new quantum supremacy experiments, sort of having the community having a new list of them, and what would be some that you would propose yourself?
Yeah, well, I am strongly in favor of that. I mean, I sort of vote with my feet. I mean, my students and I have been trying to think of good proposals for quantum supremacy experiments for the last decade, before the term was coined, even. I think that, even in the wake of Google's historic milestone, there's an enormous amount still to do. Exactly like Umesh Vazirani said in his talk this morning, right? Quantum supremacy is not a point. It is sort of an era, or a sort of cloud that we're now entering. But it would be wonderful to replicate the sort of demonstration that Google did in other hardware platforms, in trapped ions, in photonics, and so on, to do the experiment with a larger number of qubits so that you actually exceed the hard disk capacity of the Earth's currently largest supercomputer, rather than just barely fitting within it, as according to the IBM group, Google is doing right now. It would be great to do the experiment with a better fidelity. It would be great to have a service where sort of independent skeptics can generate the circuits and run those, and and also to do sort of direct classical verification of the hardest circuits. One of the ironies of IBM's paper saying, well, we could simulate Google's device with using a giant supercomputer with 250 petabytes of hard disk, is this should actually now make it possible to directly verify the hardest circuits that Google did, where without that wouldn't have been possible. So I think it really moves the discussion forward. Now, beyond that, one of the biggest open problems and the things that I would most like to see is a quantum supremacy experiment that can be done on, let's say, a near future device, 50 qubits, 60 qubits, something like that, but where there is also an efficient way to classically verify the result. Okay, so there are, as far as I know, there's one proposal for that from a decade-old paper by Bremner and Shepard. No one has really looked into it carefully. I think they absolutely should. And people should try to invent interactive protocols where a classical skeptic would generate a random looking circuit, but maybe with a little secret in it that made that would make the classical skeptic able to recognize the outputs as having come from this circuit. We've thought a fair amount about how to do that. As Umesh Vazirani discussed this morning, we do have protocols for verifying quantum computation once you get to the fault-tolerant era. Once you can actually implement post-quantum cryptography on superposition states. Okay, but what about getting a protocol where you both verify quantum supremacy, you do it efficiently, and you do it in the NISQ era? So you do it without needing a gigantic supercomputer to classically verify the result. I think that would be a major step forward in this area. And then beyond that, the obvious direction, one that everyone knows about, is do an experiment that achieves quantum supremacy on a programmable device. So solves a well-defined problem that we don't know how to solve classically, but where in addition we actually care about the answer. Okay, so do a simulation of some condensed matter system, maybe even a quantum gravity model. It's kind of crazy that one of the first feasible applications of quantum computers might be to simulating quantum gravity. Okay, but that seems to be the case. Better yet, would be to simulate an interesting molecule. Learn something about reaction rates that chemists would care about and that might even be industrially relevant. It is very, very unclear to me whether or not this can be done in the NISQ era in a way that will be truly useful, but I think it is absolutely worth trying. There's not even a question that it's worth trying. Of course, that will be a major milestone, beyond just quantum supremacy itself, right? To get, I like to say that for me, the number one application of quantum computing has always just been disproving the people who said quantum computing was impossible, right? I just, these like Gil Kalai and these others who come to my blog to argue, I just want them to, be forced to confront the reality of quantum mechanics. Okay, and quantum supremacy is great for that, but for some reason, there are some people in our community who seem to want more. So, it would be great to get that more. And then, beyond that, the next obvious milestone beyond that is, of course, a useful demonstration of quantum error correction, to keep in a fully programmable system, to keep logical qubits alive for longer than the physical qubits. So, these are the things that I think people know about and are going to be working toward in the next 5 or 10 years. But there is a lot of, I want to emphasize that there's a lot of scope for new ideas. I mean, you may have heard about this certified randomness protocol that Google is going to be rolling out, or actually trying. So this was something that I realized 2 years ago, could be done. That you could just take their quantum supremacy experiment with Sycamore and almost immediately repurpose it for this other application, and that sort of had not been something that anyone had been talking about before, right? And it just came, not from thinking about how do we get useful applications, but just thinking about what are these devices doing, and then once you starting from what they're doing, and then trying to see what else can we get from that? What could it be useful for? I would want to encourage everyone here to think of more things that could be done in the next 5 or 10 years.
Great, thank you. And you actually mentioned this first application potentially of quantum supremacy that you proposed along with Google. So you said that's rolling out soon. So who's going to be using this, and when should we expect it, and on what scale would this be?
Well, I don't know if anyone will be using it in a way where they really need to use it, right? I think so basically what this protocol is, it's a way to generate random bits. By itself, that is profoundly unimpressive. There are many, many, many much easier ways to generate random bits. But then you want to prove to a skeptic, let's say over the internet, that these bits really were generated randomly. That you responded to a challenge in a certain way, you passed the test, and you could not have responded this quickly and passed this test unless, number one, you really were using a quantum computer, and number two, your quantum computer really was sampling from some probability distribution that has a lot of entropy in it. Okay, and once you know that there's a lot of entropy, then even if the quantum computer was inserting some biases in some way, you can still use it. You can feed it into a classical tool called a randomness extractor in order to get nearly pure random bits. So that's the basic proposal. One of the key applications that occurred to us early on was for what are called proof of stake cryptocurrencies, like the next generation Ethereum. So these are cryptocurrencies that try to be a little environmentally friendlier than Bitcoin, like not use 1% of the world's electricity on inverting a hash function. Okay, but you still need trust in the system, and the way that they do that is by constantly running a lottery to decide who gets to add the next block to the blockchain. Okay, but this requires a huge source of random bits that are broadcast to everyone, and that everyone has to trust we're not secretly biased, we're not corrupted. So we have no trusted central authority. And there are all sorts of ideas that you could bat around for how to accomplish this. You could have everyone turn their telescopes to the sun and look at the pattern of sunspots and try to use that to generate a random sequence. Okay, but you need everyone to agree on the exact same random sequence. So my protocol is basically one potential way to accomplish this that involves a challenger repeatedly challenging a NISQ quantum computer, like Sycamore, to generate samples that achieve a large linear cross-entropy score, that are sort of detectably biased in a way that sort of shows you that they really did come from the quantum computer, and as a consequence that they really were sampled in a way that has a lot of entropy. Now, there are a lot of practical problems in really turning this into something useful, and maybe, the biggest one is the verifier, right? The verifier has to, if it actually wants to verify the results, it has to invest an enormous amount of classical computation time. So there's that problem. And then there's also the problem of, well, why should everyone else trust this verifier? Okay, the verifier is just a classical computer running some deterministic piece of code. So, at least we've sort of reduced the trust problem in that way. But, you may want the challenges to the quantum computer to not be generated by one party who itself might be corrupt, but to sort of be generated in some distributed fashion. And so there are a lot of issues here for cryptographers and protocol designers to think through. Okay, the one thing that we can say with confidence is that under some very plausible complexity assumptions, you do get from this a type of functionality that just would have been clearly impossible in the classical world, right? Of just getting these bits that are, certifiably random because they pass this challenge, right? In the classical world, someone always could have subbed in a pseudo-random generator, and you would have been none the wiser for it. Okay, and so now it's sort of up to us and up to the crypto community and the security community to sort of figure out what that new functionality might be good for, if anything.
Great, thanks. And on the topic of applications, so actually one of the first communications I had with Scott Aaronson was more than a year ago when I was going to give a talk on an introduction to quantum computing, and I wanted to get some feedback, so I cold emailed him and asked him for some feedback. And a couple of days later, he very kindly sent paragraphs of feedback. And one of the things he said was I started off with applications, and one of them was quantum simulations, and he said he was very happy that I had led the applications with quantum simulations, because that's one of the most promising set of applications. So I'm curious if, if that's still the same way you feel about quantum simulations, and also what are other promising set of applications that you think are worthwhile pursuing?
Okay. I think that ever since Feynman and others proposed this idea in the early 1980s, right, our best shot of doing something truly useful with a quantum computer has always been to solve problems that themselves involve quantum mechanics in some way, right? Sort of like that is what a quantum computer is born to do, right? That is what it wants to do, right? It was sort of an amazing mathematical discovery in the 1990s that you can sometimes, in some special cases, torture a quantum computer into solving a purely classical problem, faster than the best classical algorithms that anyone has been able to design. That's an amazing discovery that is justly celebrated. But in some sense, the place where it looks like the speed ups abound, where you don't have to sort of carefully craft your problem in order to get a speed up, is going to be things involving quantum simulation. And the good news is that actually is a huge application area. That actually is something that high performance computing is used for on a huge scale right now. And where there are industrially relevant many-body quantum mechanics problems that have stumped people, despite how good the approximation methods and various heuristics have become. And so, this is a place where you could have an impact. And furthermore, where it looks like you may be able to start doing something useful even in the NISC era. So, without massively expensive error correction. Okay, so this is why I still think that this is, if you're trying to get economic value, then as far as I can see, this seems like maybe still the best shot. And, the other things, we sort of all know, and we've been hearing about them all throughout this conference. There is Grover search. There is, but it's a mistake to think of these things as just like one algorithm, right? There is sort of an enormous family of problems to which, something Grover-like can be applied. Something like amplitude amplification to get either a square root speed up or something short of that, but still some asymptotic speed up. That's, a huge number of machine learning and optimization problems. There are sort of protocols where you're trying to use a quantum computer to prove something to a skeptic, and we've already talked about those, whether it's proving randomness or proving some other property. I think that there's a lot more to be done there and to be explored in that domain, right? People bang their heads for 20 years like searching for a fast quantum algorithm for graph isomorphism or for breaking lattice-based cryptography. They haven't found that yet, but in the meantime, that's caused a lot of kibitzers to complain. Well, you know, looks like after Shore and Grover, quantum algorithms research has just been a big failure, right? And you've just failed to find more quantum algorithms. And you know, my answer to that is simply, well, in a huge number of theoretical fields, you find that there are these really, really juicy, low-hanging fruits that get picked very early on. And that is sort of what happened here. But you know, when the low-hanging fruits have been picked, you know, one of the best things to do is to just start looking in a different orchard. Okay, and so, you know, looking for these sort of protocols where, you know, the quantum computer just proves something to a skeptic by doing something faster, I think is one of those other orchards where we should be looking. You know, and then, you know, there's been a huge amount of hype over the last decade or so about exponential quantum speedups for machine learning problems, you know, or potentially even for optimization problems. I confess to sort of limited optimism about that. I think that it should still, you know, it should absolutely be pursued. It should be thought about once the useful devices become available. We should try out the algorithms like the QAOA and VQE and so forth. We should see how they perform. But, you know, we ought to be clear that right now, you know, we do not have any clear-cut killer application where you get sort of an end-to-end exponential speed up for some machine learning problem compared to what we know how to do classically. Okay, we thought that we did, but you know, so some of the best candidates that we had have since been dequantized. Okay, and so I think that very much remains open. You know, on the other hand, you know, we know that there are lots of Grover type speedups, and surely there will be more of those to be discovered. You know, but besides that, I would want to just urge people to continue looking for new orchards. That is, you know, just broaden your notion of what a computational problem could even be, or you know, what type of domain a quantum computer might be useful for.
Great, and you actually mentioned Grover search, and I read that when you were a teenager, you did an internship with Grover. So I'm curious what you learned from working with him and about creating quantum algorithms and sort of, I mean, a lot of people here are working on quantum algorithms and applications, and what sort of advice do you have for them?
Yeah, so I mean, I was working at Bell Labs in some, you know, just some software internship that had nothing to do with quantum computing, but you know, I was sort of obsessively reading about it because, you know, I'd heard about it. My first reaction was, this sounds like obvious garbage. I mean, you know, this sounds like, you know, the physicists just have no idea what they're up against, right? The extended Church-Turing thesis, you know, will not just, you know, topple over like some little house of cards. You know, but then, you know, I read about it, and wow, you know, this quantum mechanics, this is really a thing. This is something of, you know, comparable enormity to the Church-Turing thesis. And so I started reading about Shore's and Grover's algorithms. How do they work? I was amazed that despite my, you know, almost total ignorance of physics, you know, an ignorance most of which remains to this day, you know, I was able to understand it because it was just linear algebra, right? And I was like, well, you know, why didn't anyone tell me that quantum mechanics was just linear algebra? And then I realized that Lav Grover worked in the same building, so I sought him out. And I, you know, excitedly shared with him stupid ideas for improving Grover's algorithm that didn't work. Then, you know, Lav was nice enough to invite me back to work with him the next summer. And you know, that summer I met Ashwin Nayak, who was then visiting from Umesh Vazirani's group in Berkeley. And, you know, I sort of found out what was happening in quantum computing theory, you know, then, and I realized, you know, wow, you know, I really need to join this Vazirani group. You know, I have to learn what they know, right? They were clearly, you know, able to solve problems that I was not able to solve. And, you know, I wasn't working on quantum algorithms as much as I was actually working on quantum lower bounds. I was trying and failing to rule out quantum algorithms. And you know, Andras Ambayanis had a major success in doing that, on one of the exact problems on which I had failed, called the and of ors, and that made a huge impression on me. So what general lessons could anyone draw from any of this? Well, I'm not sure, actually. Maybe keep trying. Maybe when if you work on something for a long time and you can't do it, but then someone else can do it, this is the time that you spent may actually not have been wasted at all, because now you're in a position to understand what the other person did, to use that to do something else, and besides that, I guess more generally, the biggest piece of advice that I would like to give people who are looking for quantum algorithms is to not sort of start with, I have some customer who needs, machine learning for oil and gas exploration. Now, how can I sort of torture quantum computing until it fits into that, preconceived idea of what it should be good for, right? I think that this strategy has been tried a lot, and the results, are not often that great. And I think that history, like if you look at Shor's algorithm, right? Where did it come from? It came from this other thing, Simon's algorithm, right? Which at the time was a completely theoretical black box construction. It was actually rejected for publication in 1994 because people said this is just obviously a useless, contrived problem. Okay, but Peter Shor looked at it and he thought differently. Okay, so I would say just start with quantum speedups. Start with clearly establishing the reality of a quantum speedup for something in an actually fair comparison against the best that a classical computer could actually do. Okay, and don't be satisfied with, I'm implicitly solving the problem. The answer is encoded into my amplitudes. No, like get an actual algorithm, where you actually measure and get an answer out, and see where you can do that. Well, putting out of your mind for temporarily what it is useful for. And then once you understand, just structurally where the speedups are, then go and think about what they might be useful for.
Great, okay, and now we can open up to the audience, so you can ask him anything.
Should you get a microphone? Okay.
Hi. So algorithms consist in a series of gates, and the question is about gates. And it might sound a little naive. How does the qubit know what to do when you give it a Hamilton gate or a Pauli gate? How does it know the difference? How does it know what to do in order to go through the algorithm? Does that question make sense? Is that?
I can maybe sort of correct it to something
Please.
that would make sense. Basically, what at its core, what quantum mechanics says is that so first of all, the state of the world is this or the state of any isolated physical system is this unit vector of complex numbers, and it changes in time by some Hamiltonian being applied to it, right? And now which gate is simply a question of which Hamiltonian is being applied at that time, right? So if you go into a quantum computing lab, what you'll see is a lot of control systems, control electronics going into the chip or the trap or whatever it is in order to precisely to control the Hamiltonian that is being applied to the qubits. The details are different in different architectures. In trapped ions, this would be a laser that is picking up the ions and moving them around. And if two ions are close to each other, they'll feel a Coulomb force, which you can then use to construct a 2-qubit gate. Okay, if we're talking about superconducting qubits, this is controlling the Josephson junction, right? That then mediates an interaction between these two loops of wire, these two transmons or whatever they are, that then changes the states of those currents. Okay, now if you you can, like with anything in science, you can always push back further, and say, why, but why that? Why that? My 2-year-old son does the same thing, right? But, you could say, okay, but why, should the why should the state of the world, change in a different way depending on which Hamiltonian is applied, right? Now notice that this question has nothing to do with quantum mechanics in particular, right? We could just as well have asked about classical physics, why does this rock move when I kick it? Why does the rock know that my foot was there? Okay, at some point these questions are going to be above my pay grade. They might require a metaphysician or a theologian or something.
Thank you.
Great. Yep,
Yeah.
down here.
So, in your own words, is there an orchard that we should be looking at where we might find juicy fruits that we're too distracted to look at right now?
I mean, if I really knew what orchard everyone should be going to next, then I would just be going there myself, right?
I have a question over here. I've been quite curious about ADS-CFT and the fact that people have been noting that error correcting codes can be sort of mapped from the surface into the bulk. And so I appreciate from you sort of an intuitive feel for why that might be true. And then the second part of my question would also be, is quantum gravity, as we start to look out, maybe be able to in the future, say, image dark matter, will that sort of lead us to those sort of other quantum information insights like the error correcting code on ADS-CFT?
Okay, my first reaction is you're asking me these questions, so I have been part of the It from Qubit collaboration that Patrick Hayden and Lenny Susskind and their friends have started. I found it incredibly exciting to listen to them, and I would say that I have at most a cartoon understanding of what is going on. I try to serve as the computer science consultant to ADS-CFT people. If they can boil down a question into computer science language, then I try to help them. But now your first question was, why should it be that there is some error correcting code, sort of underlying space-time, as these sort of recent ideas suggest that there is. Maybe one answer that I could give to that is that from very, very general considerations, we find that the number of bits or the number of qubits needed to describe a bounded physical system, a system does not seem to scale with the volume of that system, right? It seems to be much, much less than that. And one way of understanding that is simply, well, if you take too many bits and you try to pack them in too small a space, like build too dense of a hard disk, then it will collapse to a black hole. What good is that, right? A black hole is sort of the densest hard disk allowed by physics. It stores about 10 to the 69 bits or qubits, really, per square meter on its event horizon. So it's great for storage density, really bad for retrieval of the bits. That's really, really slow. Okay, but because of sort of the existence of gravity in our world, the fact that things that become too dense in information sort of collapse to black holes, you're then led to this holographic bound, related to the Bekenstein bound, right, which tells you that the number of bits or qubits that you can store in any physical system whatsoever should scale at most like the surface area, of a surface enclosing the system, and not like the volume. And then, once you know that, then, you could say it is natural to ask, well, then could this theory be dual to some theory that actually lives in a lower number of dimensions, right? So could there be some other theory on the boundary, right, that would sort of make manifest, this lower information density, right, that would sort of explain it by saying, well, yeah, there are fewer qubits because all of the qubits are actually literally are encoded on some lower dimensional space. I say that it is natural, but because this was one of the biggest stories in theoretical physics of the last several decades, and took people like Maldacena and Witten and so on to actually work out how this works. But I hope that just thinking about the amount of information sort of already gives you a clue as to what could be going on. Now, you also mentioned dark matter. I have no idea whether dark matter, what the dark matter is. Will it contribute in some way to understanding quantum gravity? Will that in turn contribute to ADS-CFT? I know that there are speculative ideas about all these things, but ask Preskel, okay? Don't ask me.
Yeah, over here.
No.
So quantum technology has advanced a lot over the past 5 years. And looking back over the past 5 years, would you say that the technology has advanced faster or slower than you might have predicted 5 years ago?
So I like to be pessimistic in my predictions in order that I can be pleasantly surprised, rather than disappointed. If you'd asked me 5 years ago, do I think quantum supremacy will be achieved in 5 years? Well, it's not a hypothetical. People did ask me. I don't remember what I said, though. That's the problem. My memory's just been getting worse and worse. But probably I would have said, well, I hope so. It's worth trying, right? That's the thing. Like, if you're a Bayesian, right, then in principle you ought to just assign a probability to every, right? You should be able to just put a number on everything, right? But I'm not sure that I really have probabilities for every, right? Like, what I have. Would I have been able to predict who would be the president of the United States? No way in hell, right? So, I'm not actually that well calibrated about the future. I find it, enough of a challenge just to correctly understand, what other people have understood in the present. With quantum supremacy, I would say by 2015 or 2016, we did have a strong indication that it was on the horizon, which was, we knew that the Google group, was aiming directly at it. And in fact, they were saying at the time that it would just be, a year or two. Okay, and now one thing that I've learned from, talking to experimentalists is that, when they tell me that for sure something can be done in, 1 year or 6 months or whatever, I don't multiply what they said by a factor of infinity, okay? I merely multiply it by a factor of 5, okay, or something like that, okay? So, I figured, okay, maybe it's not 1 year, it's not 2 years, but, it's a matter of, some years, a relatively small number of years, like, as long as I, maintain a low-carb diet, that I should live to see this. And so in that sense, ever since I knew that John Martinez's team was aiming at this, it was not a surprise to me that they would eventually achieve it. It's still incredibly gratifying to actually see it.
Yeah, over here.
So my ex-colleagues in CERN used to say for projecting this kind of unknown or things that you haven't done before, it's a factor of pi.
Okay. All right. I'll keep that in mind.
Anyway, so my question is unrelated to science, but you said that we should focus more on finding a new orchard, like developing theories instead of talking to clients and things like that. I'm not in that business, so I guess I can ask. So, but there are indeed a lot of people in that kind of industry, right, serving their clients and doing projections. So should they just stop doing what they're doing right now and wait for theorists to come up, or they should become theorists themselves?
Well, look, I also do quantum computing consulting. So I'm sort of in that business as well, right? Some of it through QC Ware, I would say, there are a lot of businesses that have, a sort of a very legitimate interest in just understanding, this landscape. Like, here is the domain that we care about. What is known about quantum algorithms in that domain, right? What kind of, which algorithms are known? What kind of speed up do they give? There may just be off-the-shelf theory that will answer those questions. In some cases, there may be new theory that needs to be done, so I think theorists are not actually that expensive, right? And so if you're a very rich company that has a question like that, it may actually make sense to actually hire a theorist to try to tell you the answer. Okay, the danger here is to get, consultants who will just tell the clients what they want to hear. Like, okay, you want quantum speed up for X. Okay, so we will torture the reality until we can tell you that there is a quantum speed up for X. Right? That I don't think of as delivering value to that client. And so I think that the sort of the most basic ground rule of this business is that the customer, ought to be prepared for the possibility of, hearing something that it doesn't want to hear, right? Like, we have no idea how to get a quantum speed up for this problem. The prospects don't look very good, okay? And anyone who is consulting in this role ought to be willing to tell a client something that they don't want to hear.
We have a question over here.
So with quantum computation and quantum information, one of the kind of takeaways is the notion that information is physical. And so then we start look at physics, and in that case, we have things like upper bound of how fast things can go, the speed of light. And we have the Heisenberg uncertainty principle giving us a lower bound on certain uncertainties. Do you think that physical principles could be utilized, or ultimately the decider in terms of lower bounds for circuits, or how quickly computation can be done?
So I am sort of skeptical that physics can be used in that way. The main problem is that algorithms do not have to respect physical intuitions. Right, so you may have I'm not just talking abstractly. Right, we've actually seen this in examples. Like people looked at random 3-sat, for example, and they said, okay, well, there's a phase transition when the ratio of the number of clauses to the number of variables, hits a certain threshold, right? And so physical intuition tells us that this is where the problem becomes hard. Right, and the problem is that may be true for one algorithm, but there may be some other algorithm that just attacks the problem in some completely different way, not sort of respecting the structure that you were analyzing, and it does much better. And in the case of random 3-sat, that in fact is exactly what happened. There was a new algorithm discovered called survey propagation. Now, interestingly, that algorithm was also based on physical intuition, but different physical intuition than the one that had guided people before, right? And so I think proving lower bounds is an incredibly hard business, right? What I like to say is that, it's like it takes some explaining to sort of show people like why these problems are even problems at all. like, P not equal to NP, right? If we computer scientists had been physicists, we would have just declared it to be a law of nature and been done with it, right? Given ourselves Nobel Prizes for the law's discovery. If it later turned out that P equal to NP, we could just give ourselves more Nobel Prizes for the law's overthrow, right? So, like asserting, for rigorously that there can be no possible algorithm that exceeds such and such running time is sort of inherently a pure mathematician type of thing to do, right? In some very, very special cases, we know how to do it using arguments based on diagonalization and other fancy techniques. We are very far from where we want to be in terms of proving lower bounds. I think that, there will be ideas from mathematical physics that will play some role, probably, in that quest, simply because, when you go deep enough into math, everything is connected to everything else, right? And just for that reason, if for no other, yes, there will be, insights from physics that will be relevant. But, trying to prove something like P not equal to NP is inherently a task of pure mathematics, right? And, if you just want to look at it like a physicist, then just declare them different and be done with it.
Yeah, over here.
So there was a paper published in Nature 2 days ago discussing the term quantum supremacy, condemning the term itself and suggesting we use quantum advantage instead. Mm-hmm. If you've seen the paper, could you comment on, or just kind of the general discussion around?
Yeah, so I saw it, but it wasn't a paper, I don't think. It was a letter to the editor.
Yeah, it was a letter, sorry.
Leonie, I don't know how to pronounce her last name, Mueck. Was one of the authors. So she had actually previously written to me, sharing her concerns about the term quantum supremacy, that it is, too evocative of other kinds of supremacy, and even that it's going to scare marginalized people away from our field. So, the first thing that I'll say is none of this is my fault. It's this guy's fault. Okay. Yeah, he's the one who's raising his hand, right? I didn't coin this term. I just use it. But the second thing that I would say is, well, it's abhorring the types of supremacy that have tragically reared their heads again in today's world, and that we all thought that the world was past. Sort of doesn't. Still doesn't, make it obvious what to do in this case, because someone might say, well, why shouldn't we reclaim this word, right? It's not an inherently racist word or sexist word. Why shouldn't we reclaim it for, a good use, right? Or say better quantum supremacy than the other kind of supremacy, right? And then you could say, well, if we change the name and we called it quantum advantage, you could say, well, look, isn't that also kind of offensive, because it, suggests, well, some people, just have inborn advantages over other people, right? It's like, okay, the thing that we're talking about really is about one thing, quantum, being better than another thing, right? Classical, and so any word that you use to describe that is going to have some connotations of being something being better than something else, and that in turn would have, if you played a game of Kevin Bacon, would have abhorrent connotations when you then applied that in the realm of people. But again. Better that we should talk about quantum being better than classical than about one set of people being better than another set. So I don't know. I don't think it's obvious. Then there's the question: what other term should be used, right? The proposals I've heard. There's quantum advantage, but that maybe sort of understates. I think Preskel was really trying to talk about a moment in history where there is a step change that happens, and I'm not sure if it really gets at that connotation. Right, I've heard quantum inimitability, that is inability to imitate with a classical computer. Okay, but how many people are going to be able to pronounce that? Right, I had to practice before I could do it, okay? I've heard quantum ascendancy, okay? But that makes it sound like we're a UFO cult, that's going to just ascend to the quantum computer in the sky. So I don't know, I think, if there's some other like really, really good term, then maybe, that we can all coalesce around, then maybe we should switch to that one. But I think it's an open problem.
Okay, yeah, down here.
According to complexity theory, so BQP and QMA are smaller than X space, but why simulator requires exponential memory?
I'm not sure I understood the question. If you want to simulate BQP classically, you don't need exponential memory, right? We know that BQP is contained in p-space, for example. That was actually observed by Bernstein and Vazirani in their paper in 1993.
Okay, we have time for one more question.
So we're coming up on the holidays, and many of us are going to go home and see family. Outside of your wonderful opening statement about studying things that can't be done on computers that don't exist, what other things can we use to tell our families when we say, what do you do, when you say, instead of saying quantum information science?
Isn't saying quantum information science, cool enough?
They may ask a follow-up.
Would be my first reaction. My second reaction would be, how close are you to your family if they don't already know? What field you work in? But no, it is good to, I think it's great to sort of practice talking to non-experts about this field, whether that's your family over the holidays, whether that's the person next to you on the plane, with their consent, of course. Whether that's, someone on the internet, a student writing to you, right? It's not just that it, gives you this warm glow that you explain something to someone, it's that it helps to clarify your own thoughts, right? If you can't explain something simply to someone else, then you probably don't understand it well enough yourself.
Great. I think that's it. Yeah, thank you very much.
Thank you so much. Thank you.
Yeah, sure.
Thank you. This was great. So I'm just going to wrap up very quickly. You're more than welcome. You don't have to stay on stage. Thanks.
Okay.
Thank you so much. Thank you. This
Sure.
was amazing.
Yeah,
thank you,
thanks
Jessica.
for
Thank
having
you. Thank you. Thanks. So I'm just going to take 1 minute of your time. Thank you very much for participating. We had amazing participation. I just checked the final number. I think we had 545 attendees over the 3 days. We can't fit all the logos in one slide, so we had to use two. This is pretty much everyone. I'd like to particularly thank the organizers for the pharma track we used on the first day. It wasn't advertised, it was actually a private track. We took 15 of the largest pharma companies that wanted to come together basically in the same room with software and hardware vendors and work on what should be the 1, 2, 3, 4, 5 use cases that field should concentrate on and drive forward with. I think it's something that was actually very successful, and we need to basically repeat it with other industries. So I'd like specifically to thank Amir Roach and his team in Takeda that put everything together for that, and Carl at Accenture. And with that, I'd like to say that all the material, or most of the material that we have the rights to redistribute, we will do so in maybe a month and a half, so it will appear on our YouTube channel, and it will also appear on the Q2B website. And mark your calendars, December 8th through 10th, 2020. We will repeat this, and now for those of you that have been with us before, you've seen how the event is growing and how the space is growing, so we expect to come back better and stronger and actually have more practical proposals like the pharma proposal, like the industry panels we put together. And finally, thank you very much. Happy holidays, enjoy the holidays, and we'll see you next year. Thank you.